Hey guys, I'm back, Unit 5, still, Lesson 6, mole problems. Our objectives for this lesson are to use proportions that are given to us to help solve mole-mole stoichiometry problems. So let's start with a warm-up. Go to your warm-up page, and what I want you to do is quickly review notes from previous lessons, try to do some practice problems on your own, come back to the video, and get started with the next topic. So first I want you to do is write the, write the general formulas for the 4 types of reactions that we learned about in the previous video lesson. Those are single replacement, double replacement, synthesis, and decomposition. Give yourself a few minutes to do that and then come back to the video. Okay, so your answers should look something like this. You should have listed your single replacement, double replacement, and your synthesis and decomposition reactions. And the general formulas, and what I meant by that are just A plus B, C. So what I'm saying here is that I have one element or reactant by itself, and that is reacting with a compound, 2 or more elements, to yield or produce a new compound and one of the elements by themselves. Okay, so you'll see 2 products, one by itself, and then a compound. Double replacement are fairly easy to recognize, considering that notice you have more things involved in the reaction. So you have 2 compounds creating 2 new compounds. Decomposition, you have a breakdown of a compound into 2 parts or simpler parts, and then synthesis would be actually creating a new compound from 2 smaller parts. All right, so let's begin the lesson. Mole problems, an introduction. This is on page 18 of your notes. And a chemical equation is basically the recipe for a reaction. Recipe, quote unquote, okay, just like we follow a recipe for baking. So the coefficients in an equation tell us the amounts of reactants and products that we need to make the recipe work. So reactants in an equation react in specific ratios to produce a specific amount of products. Below is a recipe for sugar cookies. Okay, we have 3 eggs and a cup of flour plus 2 cups of sugar is going to yield or produce or make 24 cookies. So let's simplify this to give us some ratios. We have 3 eggs, 1 flour, 1 cup of flour, 2 cups of sugar yields 24 cookies. Okay, if we mass the eggs and flour and sugar, they should in a perfect world equal the mass of the cookies. This will illustrate the law of conservation of mass. So let's say our eggs had a mass of 200 grams, our flour was 160 grams, and our sugar massed to 240 grams. In a perfect world, all of our cookies, after they're baked, 24 cookies, should mass to 600 grams. So here's a question for you. If you had to bake 48 cookies, how many eggs would you need then? All right, well, if this general recipe calls for 24 cookies and I need 48, okay, 24 into 48, that's double, okay? So if you're doubling it, then we have to double everything in the recipe. So how many eggs are we going to need if we double this? Answer, 6. Okay, we're going to need 6 eggs. Basically, you're going to double the recipe. So our general method for solving mole-mole problems, what you do is you set up a proportion using your known and unknown values, and then we cross-multiply and solve for your unknown. So here's an example for you. Set up the proportion from the question and answer above in your notes from the previous page, and we will solve this. So here is the previous proportion. Okay, we have 3 eggs, 1 cup of flour, 2 cups of sugar will give us 24 cookies. If we change this, our recipe is not going to come out right. So here's the setup. We need 48 cookies, okay, and the recipe that we have calls for or makes 24. And the question was, how many eggs? So we need 3 eggs, sorry about that, 3 eggs to make 24 cookies. So we're going to solve for x. Okay, so when we set this up, we have 24x, okay, so cross multiply, and 3 times 48, okay, which is equal to 144. So 24x is equal to 144. We divide this side by 2 to give us, or I'm sorry, divided by 24 to give us 6. And that will tell us that we need 6 E's, or eggs in this case. Okay, so this is actually how you're going to set up a mole-mole problem, same exact way. First you have to look at the equation, the coefficients, and use that as our proportions with relation to what they want us to solve for. Okay, so here's another example. If you have 10 eggs and an infinite amount of sugar and flour, what is the greatest number of cookies that you can make? So it doesn't really matter how much. They're saying we have as much as possible. So we're going to figure out how much or how many cookies we can make with just 10 eggs. So we're setting up the proportion. 3 eggs to make 24 cookies. So now we have 10 eggs. How many cookies can that make? Okay, so again, cross multiply, we have 240 and then 3x. Okay, there's the x. Divide this side by 3 and you should get, okay, 80 cookies with their infinite amount of flour and sugar. So we can use the process we used with this cookie recipe and apply it to chemical equations. And like I said before, the only difference is we always check to make sure we are starting with a balanced chemical equation. This is very, very important. If it's unbalanced, then therefore we cannot use those proportions because they're not correct. That would go against the law of conservation of mass, conservation of matter, and conservation of charge as well, okay? Balanced chemical equations always. Example 3, which is a chemical formula here, or chemical equation. So let's look at this one. And the question says, or states, how many moles of nitrogen gas would be needed to produce 10 moles of ammonia? Well, here's our general formula, okay? So this would just be like our recipe, okay? Just make sure that the equation is balanced. So we have 2 nitrogens here, 2 here, 6 hydrogens, 6 hydrogens. So the formula or the equation is balanced, so we can go ahead and try to set up our ratios. So we have 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of NH3. So those are proportions, all right? What we're solving for is this part, the N2, right? We need to know how many moles. So that's going to be our X. So X over 1, okay, will tell us our proportion for moles of nitrogen gas is going to be equal to how many moles are going to be produced using 10 moles of ammonia. All right, so if we use 10 and the original setup is 2, so here's our original ratio. For every 1 mole of nitrogen gas, it produces 2 moles of ammonia. Okay, we have 10 moles of ammonia, so how many moles of nitrogen gas are needed? So let's do our crisscross or our cross multiplication here. So we have 2x is equal to 10, okay? And then we divide that by 2. X is equal to 5 moles of N2. Okay, so just checking to see if you're watching my video, answer this question for the warm-up in class. What day of the week is your chemistry midterm? Okay? That is the secret question of the day. All right, and back to practice now. So mole-mole practice. Let's use the following equation to answer the following questions 1 through 3. So let's just double check to make sure that the equation is balanced. We have 3 carbons, 3 carbons, 8 hydrogens, 10 oxygens, and 4 here plus 6 is 10. Okay, so our equation is balanced. So the question is, if 12 moles of C3H8, and it's underlined to tell you what we're trying to figure out. So let's set up our ratios here. We have 1, 5, 3, and 4. So those are the proportions needed to double, triple, whatever we're going to do to this quote-unquote recipe. All right, so we're looking at the C3H8. So 1 mole of C3H8 is needed to produce 4 moles of water. Okay, so we want to know how many moles of water are going to be formed if we have 12 moles of the C3H8. So if we have 1 mole to every 4 of water, okay, and then we say we have 12 moles of C3H8, how many are we going to need here? So let's cross multiply, and we're going to have x equals 12 times 4 is 48 moles. That's it. That's all we have to do, set up the proportion. So we need 48 moles of H2O. Next question says, if 20 moles of CO2 are formed, then how many moles of O2 are reacted? So I'm going to scroll up a little bit, look at our proportion. Okay, next question, if 20 moles of CO2 are formed, then we want to know how many moles of O2 are reacted to form that many moles. So then we'll set up our proportions that way. And I just have to fix my pen here really quick. Okay, so let's look. We have 20 moles of CO2. And let's look for CO2 here. And the ratio or the proportion is 3 for that. So we got to look at the O2 side. How many are produced for every 3? That would be 5, so that's going to be in the bottom. And this is what we're solving for. Okay, it's the after the fact. If we change our numbers, that's going to be together either on top or on bottom. Okay, so 20 times 5 is equal to 100, so this would be 3x equal to 100 divided by 3. So our x is going to equal approximately 33.3 moles, but with sig figs, this is going to equal 30 moles. All right, so it says how many moles of O2 actually reacted. Approximately 30 moles of O2 react in order to form 20 moles of CO2. Okay, number 3, if 8 moles of O2 react completely, how many moles of water are formed? So here we go. These are the numbers that we're looking for to set up in our ratios. So we have 8 moles of O2. Okay, so that would be an 8 to 5 ratio according to this for O2. So we are going to set that up, 8 to 5, and then generally in the equation 4 moles are produced, so that's going to go on the bottom. We want to know how many are formed if we change the number to 8. Okay, so this would be 5x equals 32, and we're going to divide that by 5, and our answer will be about 6 moles to sig figs. Okay, so we have 6 moles of H2O formed when we use 8 moles of O2. So this is the same concept as the baking concept. Okay, we have ratios, we have to make it equal so that the reaction can work. All right, so let's look at a couple of other ones here, and then we're going to be finished. So use the following equation here. N2 plus 3H2 gives us NH3. So that's nitrogen gas plus hydrogen gas will give us ammonia. Let's double check to make sure that it's balanced. So we have 2 N's, 2 N's, 6 H's, 6 H's. We're good. 4. If 2.5 moles of N2 react completely, how many moles of NH3 are formed? So let's set up our ratios. This is actually going to be 1, 3, and 2. Those are the proportions of our reactants to form that amount of product. Okay, so this would be like 1 cup of sugar plus 3 eggs gives us 2 cookies, right? Makes no sense, but still, we're saying 1 mole of nitrogen gas and 3 moles of hydrogen gas will always produce 2 moles of ammonia. So if we have 2.5 moles of N2, then we have to figure that out. Okay, so let's set this up. So we have 1 mole of nitrogen gas. We know it will produce 2 moles of NH3. So we know that. So we're going to set that up. Now, on the bottom now, if we change our numbers, we're going to have 2.5 moles of NH2, or N2, I'm sorry, N2, to produce how many moles of NH3 now? So we're going to set this up. Now this is going to be X equals, cross multiply, 2 times 2.5 is 5. Simple. 5 moles of NH3 are formed. 5. If 9 moles of NH3 are formed, then how many moles of H2 are reacted? So this is what we're dealing with, these numbers. Okay, so NH3, let's look at that. The proportion is 2, and that's going to equal or give us how many do we need? 3 hydrogens. Okay, They give us 9 moles of NH3, so that goes on that portion of the equation, and 3 over X. That's what we want to know, how many moles of H2. So that's the H2 side right there. Okay, so 2 times X is going to equal 9 times 3, which is 27. 18, what am I thinking? 27. Okay, we divide that by 2, and with sig figs, X is going to equal 14 moles. Okay, now number 6, if 3.5 moles of NH3 are formed, how many moles of N2 react? Again, let's look. We're talking about NH3 and how many moles of N2. So we have to look at that portion. N2 is 1, okay, for the N2 side, and we want to know how many. So we're going to put an X there. NH3. So for every 1 mole of N2, we get 2 moles of NH3, and they're telling us that we have 3.5. So we're going to see how that changes, how much N2 we need. So it would be 2X equals 3.5 divided by 2. So X is going to equal 1.75 moles of N2. 7. How many grams of N2 are reacted when 3.5 moles of NH3 are formed? So here we go. This was a little trick, but it says how many grams. So we're going to have to use a conversion of, or a mole calculation here. Okay. So we have N2 are reacted with 3.5 moles when they're formed. So this is actually going to use the answer from number 6, because we're talking about 3.5 moles, and we're also talking about N2. So using this information, if we know we have 1.75 moles needed for N2, we need to find grams. So let's use our equation. All right, number of moles equals grams over GFM. So we have our number of moles, 1.75 moles, equals, okay, and we need to find the grams over whatever the GFM is of N2, which is 2 times 14.0067. Okay, so when I put that in there, I get my GFM, so it's 1.7 times, okay, and I don't know why I put equals, but 1.75, right, is equal to our grams over our GFM, which is about 28. Okay, so 28 times 1.75 will give you about 49.0 grams of N2 needed. Okay, so please jot down any questions that you have on these ratios, proportions. Okay, go back to the lesson, pause it, rewind, listen to my voice explaining how to set these up. So for homework, what I'd like you to do, or continue to do, is some practice on your own in your practice packets on page 22. Try some. Do some practice.